In this video, we're going to look at an example where we can start to understand the BiPlot from a more complicated example, but still something that we can view the original data and intuit what's going on in the BiPlot. The data for this example will be consumption of food and drink across the UK. And these numbers in this table are the grams per person per week on average for individuals in England, Wales, Scotland, Northern Ireland for the foods and drinks along the rows. Now, we can standardize the rows of this table because, we wouldn't expect the grams of confectionery to be the same as the grams of meat or vegetables. We hope that people would eat more good foods than they did confectionery. So we can standardize this data and then look at a heat map and see how the countries are different in their consumption. For example, some of the things that might jump out: in Wales, much more likely to drink beverages and eat cereals. Also, sugars, fats, and oils are kind of highlighted in the column Wales, where everything else is blue or white. Carcass meat in Northern Ireland is more popular, along with fresh potatoes. So that information is exactly the same information we're going to reveal with the BiPlot, which is not to say the BiPlot is a better visual for this information. It's just, it will be for much larger data sets. So to start with, we're going to opt for the transpose of that table you just saw, where we use the rows to be the countries and the columns to be the foods. And this is just done with the transpose operation on the data set. So the head function just prints out the first 5 observations. Of course, I only have 4 here, so it printed the whole data set. And I'm reading this data set directly from my website. We can then compute the principal components of this data. And I recommend the prcomp function for this. And you just input the data table. You could specify a certain number of columns if you didn't want everything. Here, we want all the columns to go into the PCA. And in order to make this a correlation PCA, I've used scale equals true. Now, let's just look at the output object, PCA, in our environment and the different components of it. One thing I should point out already is this equals sign. Now, if you're classically trained in R programming, you probably use 2 character strokes to use the arrow, store arrow. I don't. I use an equal sign. It's equivalent in almost every possible scenario, except scenarios that are pedantic and probably shouldn't even be used in good code. So you can join me in the equal sign revolution and just dump 2 character strokes for 1. Okay, off my soapbox. Here, the first thing in this output is a list of 4 numbers, and it's called SDEV. The second thing is a 17 by 4 matrix called rotation. I'm going to skip the next 2 and go straight to the last, which is called X, and it's a 4 by 4 matrix. Now, I've told you in the past, if you're really familiar with the loadings and the scores, you can intuit what you're looking at in any PCA output just by looking at the dimensions. Since we had 4 observations here, we would be looking for a 4 by 4 matrix for the scores. We would be looking for a 17 by 4 matrix for the loadings because we had 17 variables. And then we must have 4 numbers somewhere that are the eigenvalues. Now, these are not actually the eigenvalues. Here, they're provided as the square roots of the eigenvalues. So they're the standard deviations of the principal components. They're actually singular values. So there is a reason why those are provided that way, and we'll talk about that a little bit later. Again, the rotation matrix would be the loadings, and X gives you the scores. Center and scale are outputs that actually will tell you what the data was centered upon. So it would give you the mean vector for center. And if you do scale equals true, you'll get the the vector of standard deviations. Next, we can get some of the basic information, like the eigenvalues and the proportion of variance explained from summary function. So if we look at the summary of our PCA, I see this first table, which would give me, again, the standard deviations, the square roots of the eigenvalues, the proportion explained, and the cumulative portion. So from this table, I can see with two principal components, I'm already explaining 93% of the variance. And with the third component, I'm pretty much explaining everything there is. And the basic plot function, just plot of PCA, I've added a title here, but if you don't add the title, if you just do plot PCA, you would get this bar plot, which is essentially a scree plot because it's just showing the variances in descending order. Now we can use the scores to show the projection of the data onto 2 dimensions. Remember, these were 4 countries along 17 dimensions, so they started as 17, they started in 17 space, and I've projected them here into 2 space. And everything here is just to make the plot a little bit prettier. This text function actually writes the names of the countries. This is the coordinates that it wants me to write the text, and then what text does it want me to write. The row names are what gives the country names. Now, from this graph, there's not a whole lot I could intuit. I would know that England is more like Scotland than Wales is, because England is closer to Scotland in the projection than Wales is. And the same with Northern Ireland. So Scotland and England look like they're probably the most similar here, followed by England and Wales. But the really interesting conclusions will be drawn from the BiPlot here. So this is the projection of all of the original variables onto the same space that the observations are projected onto. And so from this, you can understand the relationships between the location on this plot and the original variables. So to help me walk through this, I'm going to bring up the original data set heat map. And let's just start with processed potatoes. I can see that arrow is kind of pointing away from England, Wales, and Northern Ireland and towards Scotland. And if I look at my original table, I see that Scotland is much more likely to consume processed potatoes than the other 3 countries. Similarly, if I look at fresh potatoes, that points down towards Northern Ireland. Wales is also kind of in that direction. Now, you might not see Wales in that direction, but I do, because when I think about this direction, I think about kind of moving along that direction on a plane. Okay, so if you just observe this green line that I've placed here, moving in this direction means my observation is kind of more towards fresh potatoes in this sense. Okay, so Wales, I kind of hit Wales first as I move along that fresh potatoes axis, and then Northern Ireland is really far along that fresh potatoes axis. And that's the same conclusion I would draw if I were to look at this data. The smallest is Scotland, then England, then Wales, then Northern Ireland. And that is, you know, how you would encounter those observations as you moved along, as you move that green line in both directions. Okay, similarly, Wales. Similarly, I would conclude that Wales is more likely to consume fats and oils, cereals, processed vegetables. There's processed vegetables, cereals, fats and oils. Sugars is in there, it's a little hard to read. Fish also will be dominant in Wales versus the other countries. Soft drinks, I would expect to see Scotland kind of taking the cake. And I do, followed by Northern Ireland, again, because we're moving like a plane along that direction. Okay, so England would be kind of in the middle. England's kind of in the middle on a lot of these. And moving out, soft drinks would be, I would hit Scotland last. Carcass meat, very much a Northern Ireland phenomenon. All right, so that's the interpretation of the BiPlot. You can stare at this for a little while and convince yourself that all of these things will line up and work. It's really pretty cool.